Hello, everybody. Welcome back to Math 251. Last lesson, we took a brief intermission from derivatives to talk about some applications of derivatives, but today we are back to learning about different derivatives that we can find. First of all, though, our mathematician of the day is Shakuntala Devi, who was an Indian woman known as the human computer. She computed the cube root of this super long number faster than an actual computer and beat another actual computer in her calculation of the 23rd root of a 201 digit number. That is amazing. Wow. And did you know that the word calculus is derived from the Greek word pebbles due to the fact that Pythagoras used pebbles to signify numbers while working on equations? I am definitely glad we don't have to use pebbles anymore. So we know how to take a fair amount of derivatives at this point. We know how to take derivatives of polynomials, products of polynomials, and quotients of them, as well as trig functions and e to the x. Today we are going to add to our repertoire to discuss how we can take derivatives of composite functions. Now, at first, this is going to look a little bit complicated and overwhelming, but fear not, it's not actually as bad as it looks once I write it down. So this is known as the chain rule, and we use the chain rule when I have composite functions. So suppose y equals f of u is differentiable at u equals g of x. So we have this function that looks like f of g of x. We also suppose that u equals g of x is differentiable at x. Then the composite function f of g of x is differentiable at x, and its derivative can be expressed in two ways. The first way is dy dx, that is the derivative, is equal to dy over du. This means we take the derivative of y with respect to u, treating u as the variable, times du over dx. That is taking the derivative of u, treating x as the variable. So I'm going to call this the first way. The second way is the derivative of f of g of x equals f prime of g of x times g prime of x. I'm going to call this one 2. I think most of us will prefer the second one just because there is a little less room for error here. Both of these, however, are mathematically equivalent, so we can use either one. Again, I know this looks a little bit strange and maybe confusing at first, but once we do some examples, hopefully it will clear things up. So to use the chain rule with a function y equals f of g of x, we have some steps that we need to take. We first identify the outer function f, and the inner function g. Identify the outer function f and the inner function g. And we set u, a variable u, equal to g of x. So u is basically just acting as a dummy variable here. Next, I replace g of x with u to express y in terms of u. So this will give us something like, instead of having y equals f of g of x, we'll have y equals f of u. Then if I am working with equation number 1 that I just wrote above, then I will calculate the product. Dy over du times du over dx. We'll go through an example where we do this. And then my last step is I replace u, oh shoot, sorry about that. I replace u with g of x in dy du to obtain dy dx. So again, I know this is a lot of different variables and a lot of different derivatives. Fear not, once we do some examples, I think it will clear things up a little bit. So in our first example, we want to use the first equation, this guy, in order to find the derivatives of these two functions. So I have two different functions here. My first one is y equals 3x minus 2 to the power of 5 halves. So my first step is I need to identify the outer function f and the inner function g. So usually my outer function will be some sort of power. Here f is equal to x to the power of 5 halves. G, my inner function, equals 3x minus 2. If you're confused about which one should be f and which one should be g, play around with it for a little bit and then test f of g of x to see if you get your original function. And then I set u equal to g of x, which is 3x minus 2. So this is step number 1 here, this guy. Next, I replace g of x with u to express y in terms of u. So this gives me f of g of x is now equal to f of u. So this means I have 3x minus 2 to the power of 5 halves. This is f of u. Step number 2. Now I need to find, oh, sorry, this is f of g of x. So this is, in other words, u to the power of 5 halves, since I replaced my u with 3x minus 2. All right. So I have u to the power of 5 halves. That is step 2. Next, I need to find dy du and du dx. So I have u to the power of 5 halves. Since this is equal to f of g of x, this u to the power of 5 halves is equal to y. All of these are equivalent to each other. So if I wanted to find dy du, this is the derivative of this expression right here in terms of u. That means that we're treating u as the variable. We're treating u like x. So to take the derivative of this, I need to use the power rule, which means that I bring that 5 halves down in front, and then I lower my power by 1. So that's dy du. I also need du dx. So this is the derivative of u. In this case, the u is 3x minus 2, treating x as the variable. So the derivative of u, that's the derivative of 3x minus 2, is just equal to 3. So then if I take the product dy du times du dx, this is equal to 5/3 u to the power of 3 halves times 3. Whoops, 5/3. I don't know why I wrote 3. 5 halves. 5 halves. There we go. And then if I combine these two constants, I get 15 halves u to the power of 3 halves. This was step 3, finding the product of dy du and du dx. My last step is I need to replace my u with this expression right here. So I see that dy dx is equal to 15 halves u to the power of 3 halves, and I know that u is equal to 3x minus 2. So this is my derivative. Again, I think most of us will prefer method number 2, which we'll do in the next example, but I do want to show you the two different methods. All right, let's go on to the next example where we have y equals sine cubed of x. So I have my outer function. Again, it's usually a power. So here my outer function is x cubed. My inner function is sine of x. And I set u equal to g of x, so u equals sine of x. Step 1. Next, I replace g of x with u to express y in terms of u. So right now I have y equals f of sine x, but I set sine x equal to u, so this is f of u, which is equal to u cubed. So here I simply am expressing y in terms of u. This is step number 2. Now I need to find dy du and du dx. So dy du is the derivative of this guy treating u as the variable. So the derivative of this is 3u squared. And then I also need du dx. That is the derivative of u, which is equal to sine of x, treating x as the variable. So the derivative of sine of x is equal to cosine x. And now I need to figure out the product of dy du times du dx. That is 3u squared times cosine x. I can't really simplify that anymore. That was step number 3, calculating this product. And then finally, I replace my u with what I set it equal to in the beginning. So I see that dy dx equals 3. U was sine x, so I have 3 sine x squared times cosine x. And this is my derivative. This last step is step 4. So there's a lot of different variables going on here, which I know can be a little bit tricky. So let's try the next couple of examples using method number 2 here. And I think most of you will like this one, find it a little bit more approachable. So I want to use the second method to find the derivatives of these two functions. So let's do it. I have two functions here. My first step is to find my inner function f and my outer function g. So I have f of x, my outer function, and the first one. Let's write the function down actually. So I have y equals 5x to the power of 4 plus 4x minus 2 to the power of 9. So my outer function is x to the power of 9. My inner function is 5x to the power of 4 plus 4x minus 2. And we know this, so the second equation here is dy dx of f of g of x is equal to f prime of g of x times g prime of x. So I need to also find, in addition to f and g, I need to find f prime and g prime. So f prime of x, using the power rule, is 9x to the power of 8. And g prime of x is equal to, using the power rule, we get 5 times 4 is 20, lower the power by 1, plus 4. So then dy dx of 5x to the power of 4 plus 4x minus 2 to the power of 9 is f prime of g of x. So that means that I take my f prime, which is 9x to the power of 8, except since I'm not taking f prime of x, I'm taking f prime of g of x. I replace wherever I see an x, I replace that with the function g of x. So this will be 9 times 5x to the power of 4 plus 4x minus 2 to the power of 8. So this is f prime of g of x. So again, I replaced wherever I saw an x in the function of f prime, I replaced it with g of x. And then I multiply this by g prime, which is 20x cubed plus 4. So there are a lot fewer variables in this method, which is why I think a lot of us prefer it. If you were to try this example with the method that we used in the first example, you'd get the same answer. It would just be a little bit different, the process. All right, let's do the next example. So we have y equals the square root of 3x squared plus x. Another way to think about this is 3x squared plus x to the power of 1/2. So I need to identify f and g. So f of x, here my outer function is the square root of x, or x to the power of 1/2. My inner function, g of x, is equal to 3x squared plus x. Again, usually my outer function is a power, and the inner function is the stuff inside of that power. Then I need to find f prime and g prime. So f prime of x is equal to, using the power rule, 1/2 x to the power of negative 1/2. And g prime of x equals 6x plus 1. So then dy dx of the square root of 3x squared plus x is equal to f prime of g of x. So I take my f prime, except I replace the x with g of x, 3x squared plus x to the power of negative 1/2. This is f prime of g of x times g prime. If you wanted to, if the negative exponent bothers you, we could rewrite this as, since that negative exponent will end up on the bottom, we could rewrite this as 6x plus 1 over 2 times the square root of 3x squared plus x. But if you left it as is right here, that would be okay too. All right, I would like for you to try example number 3 on your own using either method that you prefer. So go ahead and give example 3 a try. Pause this video and try it by yourself. All right, hopefully you've taken the time to try this. So here I have two functions again. And because I think most of us prefer the second method, I will go ahead and use the second method. So I have the function y equals 7x squared over 2x plus 2 to the power of 3. My outer function is f of x equals x cubed. My inner function is 7x squared over 2x plus 2. Now I need to find f prime and g prime. So f prime is equal to 3x squared. Now to find g prime, I'm going to have to use the quotient rule since I have a quotient of two functions here. So g prime of x is equal to low d high, the bottom times the derivative of the top, minus the top times the derivative of the bottom over the bottom squared. That is g prime of x. You could simplify it if you want to. I'm just going to leave it like that. So then f prime of g of x times g prime of x is equal to, well, f prime was 3x squared. I replaced that x with g of x, which is 7x squared over 3x plus 2. This is f prime of g of x times g prime, which is this monster right here. 2x plus 2 times 14x minus, if I multiply that 7 and that 2, I get 14x squared. All of this over 2x plus 2 squared. This is g prime. So hopefully you're kind of finding the rhythm of this method. Basically, we take the derivative of the outer function and multiply it by the derivative of the inner function. That's basically how this goes. All right, the next example was e to the negative 4x. Here, this is a little bit different because our outer function here is no longer a power. It's actually our exponential function. So, if I have y equals e to the negative 4x, here my f of x is e to the x, and my g of x is negative 4x. Again, if you're confused as to which function is the outer function and the inner function, play around with it for a little bit and test it out to see if you get the right function. This means that f prime of x is equal to e to the x, and g prime of x equals negative 4. Then f prime of g of x is equal to e. I replace the x and the f prime with a g of x, so that's e to the negative 4x times negative 4. I like to write the constants in the front, so this is negative 4 e to the negative 4x. This actually leads to a pretty important rule that we will see over and over again in this class, and that is the following. The derivative of e to the kx, where k is any number, is equal to k times e to the kx. We will see this all term. So you could just use the chain rule every time we see a function like this, but you'll always get this answer, ke to the kx. All right, next we have more of a conceptual problem, and actually there is a typo. There is a row missing here, so draw in this row with me. I have 3 here, 5 here, 8 here, and 2 here. My apologies. So I want to use these values to calculate h prime of 1 and h prime of 2, given that h of x is equal to f of g of x. So if h of x is a composite function, f of g of x, then I know that h prime of x, using the chain rule, is f prime of g of x times g prime of x. That's just using the chain rule. Since I have a composite function, the derivative, we have to use the chain rule. So h prime of 1 is f prime of g of 1 times g prime of 1. And now I need to look at my table to see what g of 1 and g prime of 1 are. So this is f prime of g of 1 is 3. G prime of 1 is 6. Okay, well now I have to look at what f prime of 3 is. F prime of 3 is 5. So this is 5 times 6, which is 30. If I wanted to look at, just erasing these circles real quick, h prime of 2, this is f prime of g of 2 times g prime of 2. So I need first to find g of 2, which is 2. So that's f prime of 2 times g prime of 2 is 3. And f prime of 2 is 6. So this is 6 times 3, or 18. So we don't necessarily need functions in order to use the chain rule. Here we didn't have functions, we just had some tables of values, but it still worked just fine using the chain rule. All right, so we have one more theorem that we've already seen today, actually, and one more example. So this kind of gives us an easier way to use the chain rule if I have a power function. So if g is differentiable for all x in its domain and p is a real number, then the derivative of this function g of x to the power of p using the chain rule is equal to p times g of x to the power of p minus 1 times g prime of x. This is just a specialized version of the chain rule. So you don't have to commit this to memory or anything since this is just part of the chain rule. But we've actually seen this here in a couple of examples above. We saw it in example number 3, this one. And it looks like I forgot a squared on this one, didn't I? Sorry about that. So this is an example of the power rule since I have a function raised to a power. We also saw it in both of the examples on example number 2. So this is just a, more specific way to use the power rule. So basically I take the power, I put the power in front, lower the exponent by 1, and then multiply by the derivative of the inside function. So I have one more example here. I want to find the derivative of sine of x plus 3 to the power of 13. Well, here my power is 13. So using the fact that the derivative of g of x to the power of p is p times g of x to the power of p minus 1 times g prime of x. This will be 13 times g of x. Our inner function is sine of x plus 3. And then p minus 1 here will be 12. And then I have to multiply by the derivative of the inside function. So that is the derivative of sine of x plus 3. And the derivative of sine of x plus 3 is cosine x. And that's it. But again, if you use the plain old chain rule, you would end up with the same answer as well. So I want to end this by writing down a super brief summary of the chain rule. That will hopefully help you out a little bit. So the chain rule is basically the derivative of the outer function times the derivative of the inner function. This is a good way to think about the chain rule. If you are struggling with determining which function is the outer function or the inner function, maybe I will send out some resources on that because it is pretty important with the chain rule. Of course, practice makes progress, so practicing all of these problems on the online homework will hopefully help you to figure out an easy way to determine the inner and outer functions. But that is it for today. So have a wonderful day, and I will see you on Friday.